Hi, welcome to our presentation. Thanks for the introduction. I'm Dujuan from TU Eindhoven, assistant professor there. Today I'm going to present the work together with Luuk, part of his master graduation project. Before I move on to introduce our main research question, I would like to give a bit background information why we are going to do this research. In response to the climate change and the Paris Agreement, Netherlands has set this target to reduce almost 50% of the CO2 by 2030. And to reach this target, the electrification is one of the main strategies they took. During the past 10 years, you can see that the share of the renewable energy in the gross final energy consumption has been dramatically increased from 4% to almost 20%. On the left side, this picture, you can see the peak of the capacity map in the Netherlands from this year. You can see most of the Netherlands is in red, which means that there is a waiting list of the grid connection. And only the orange one is going to be a waiting list. The light yellow one is the one areas without a waiting list, which do not have a directly critical consequences for the residential part, but already have a quite strong constraints for the residential buildings, which has been newly built, that they cannot be connected to the grid nowadays in the Netherlands, which is a huge problem. Therefore, peak shaving is more of the hot topic in the Netherlands. As a solution, there are several case strategies, such as reducing the electricity demand during the electricity usage peaks. But more common strategy is trying to decoupling from the production, also from the consumption. Especially in the residential areas, energy storage system seems like a most promising approach in the Netherlands to be promoted. However, there is no successful business model so far if you think about each individual residential buildings to install an energy storage system, and also the government would not prefer that in that direction and would like to promote the energy community in order to have this collective storage systems, which is more sustainable over the long-term profit perspective, offer systematic benefits in a neighborhood level. Therefore, this study's main research question is to how to design and develop a decision support system for the energy community to guide them in selecting the appropriate energy solution. We follow the design science methodology approach, have the 3 key steps. It's also interactive loops. First of all, to investigate the problem based on literature study and also interviews with the relevant stakeholders. And the second is to development. In this case, we are integrating the simulation and also Excel tool development together. The third is tool validations to have interview done by to check the system's usability and usability scale. So after the interviews with the relevant stakeholders in the Netherlands, including the grid connectors, grid operators, the electricity producers, and also the government and the energy community stakeholders, we found that so far, despite the technological advancement, stakeholders still lack efficient decision support systems to guide them in selecting the most appropriate storage solutions. Especially in the 2 perspectives they are lacking. One thing is that they lack the sufficient incorporation of the demand side knowledge. And secondly, as you can imagine, the energy communities lack a lot of the technical sufficient support to understand the key performance and especially how their peak will be shaved, the peak shaving potential in a neighborhood scale. So therefore, for this study, we're particularly targeting on these 2 problems, and to develop system architectures of the decision support system to tackle these 2 problems. So the upper part is about demand simulation layer. I think you already heard many presentations in this conference about this information, building information modeling to energy information modeling, etc. And we took also a little bit simplified approach to integrate of the meteorological data, the weather data, the building information data, and also the occupant behavior data. In this case, is deterministic occupant behaviors of this profile personas in the Netherlands into the energy demand simulation. We used the design builder here and simulated the demand of the household level. And we also did the calibration of the results based on the annual data. The second part is interaction with the end users. Here is the stakeholder of the energy community that we try to make a level that they could easily understand what we are presenting to them. So we allow them to give additional input to select what kind of house they have, what kind of profile of household they are there. And we also try to explore whether there is possibility they can input smart metering data. Of course, there are privacy issues that is a big challenge. And after the results built on our demand simulations, we store them in a knowledge base, and then we integrate it in the integration layers and makes analytic engines to have combined models for the thermal energy storage solutions and also the battery energy storage solutions models, and to present them as a kind of figures to show them the final results, help them to understand what's the potential of the peak shave. As a demonstration purpose, we use a case study in the Eindhoven to demonstrate how this decision support system works. And we selected one areas based on the two main criteria. First of all, the area has more of the ownership of the house. And the secondly, that the energy label should be around rated C or lower, which means that they have a high potential to do the renovation of their households. And we select area in the source of the Eindhoven. Demonstration purpose, we use 3 types of household living in the corner house to simulate their energy demand, and which are the corner house with 2 adults, 2 seniors, and also nuclear families. And we also simulated their PV generations, a typical winter week and also typical summer week. We tested 3 lithium battery scenarios using this system, which is a moderate peak shave scenario. Also have 2 sub-scenarios with different storage efficiency. One is 85%, one is 80%. The second is more aggressive peak shaving scenario that they want to shave the peak to reach a lower baseline powers and faster. The third one is a conservative peak shaving scenario with a higher baseline power and also a bit discharging power relatively low. And we demonstrate the scenarios with a table, but also with figures in the paper, that we found that the energy efficiency, storage efficiencies do have impact on their peak shave potentials in total. And, but of course, as we expected, the conservative peak shaving strategies could lead to more peak shave potentials in this case, which is quite consistent with what we expected. This is a kind of user interface that we developed in the end with Excel. And so on the right side, this is a case study that the users, the stakeholders can put in their information according to their neighborhood or energy community information, including how many corner house, how many attached apartment or terrace apartment with different type of households. And they can also indicate how many solar panels has been installed in this kind of, in their neighborhood. They can select a day of the week or also the seasons to explore the different scenario of the peak shaving. On the left is the KPIs that the most of the likely they received from the energy storage technical companies, that they gave them these indicators about different energy storage KPI situations. Then they can also explore that based on these indicators, how in their neighborhood the peak shade potential would be. And on the left bottom, there is figures that we demonstrate to them how, for example, for the blue part is the shaving of this potential of the peak. We particularly focus on the evening peak. So in the end, make a short conclusion here that as we indicated, the two problems that we try to investigate in this research, that we basically achieved it. We integrated the household-specific electricity demand and also their PV generation into this decision support system. And we evaluate these three battery scenarios and offer the explorative values in this grid stress mitigation and local energy planning. Of course, we have to acknowledge quite a lot of limitations for this explorative research so far. And we have simplified the load profiles, and considering this heat cooling demand has not been fully integrated in the scenarios because the future scenario of the off-gas in the Netherlands would lead to more options that we have not explored yet. And also we need to scale up this decision support system to a larger neighborhood and a longer time frame to test whether it still works well. Okay, thank you for your listening, and I'm happy to receive any questions. Thank you.